This is Professor Jimenez. Today we're going to see the oscillator module embedded in the PIC Micro 1619. Okay, this is an overview first of the oscillator module, which has a wide variety of clock sources and selection features that allow it to be used in a wide range of applications. So there are different sources with this clock. Those selectable sources are these ones. You can work with an external or internal source via software. It has a two-speed startup mode, a fail-safe clock monitor. So if this is interesting for critical applications such as biomedical applications, and it has an oscillator startup timer that ensures the stability of the crystal oscillator sources, and it also has the following features. Let me point them right here. This oscillator module can be configured in one of the following modes, or clock modes. This one, which is ESL, ECM, ECH, and once we will use internal INT-OS or internal oscillator, which can go from 31 to kilohertz to 32 megahertz, and number 5, the HS or high gain crystal or ceramic resonator, which can work from 4 to 10 megahertz. So those are the two main clock we will use, the internal OS or the HS. In most of the practices will be this. I recommend the HS, the crystal, for temperature dependent applications, for industry floor applications where you don't want the clock to vary because of the operating temperature. In that case, you have to work with crystal that can withstand temperatures of up to 80, 90, or even more than 100 Celsius degrees, depending on your application. And so in these modes, now we will see the block diagram, the clock block diagram. So right here you can see it, and I will refer first to this one. There are two modes, primary modes in the oscillator: the clock input, these pins, clock input, clock output, where you can read your clock, or you can have the oscillator 1 and oscillator 2 when you can connect crystal oscillator. If you have an external oscillator signal, it'll be applied to OS1 or clock in. So this is a primary oscillator block, and then the signal comes here with this multiplexer with these pins 0, 1, and 2 with 3 pins. You can select these channels, whether you're working with the primary oscillator, or if you are willing to feedback the signal from this oscillator, from the internal oscillator. If you want to send it over there, that's where it goes. And the 4x PLL is a phase lock loop which multiplies by 4 the frequency you are getting here. So if you are applying a 4 megahertz crystal, you can multiply times 4. But remember, the 4 megahertz crystal is divided. Internally, the frequency is divided by 4. So that's how you get your frequency. For example, if you are working with a 4 megahertz crystal, divided by 4 is 1 megahertz, and the reciprocal of 1 megahertz is 1 microsecond. So that way, you know, every assembler instruction will require, most assembly instructions will require 1 microsecond, and a few of those set of instructions require 2 clock cycles 2 microseconds. So working at 4 megahertz, if you want to increase the speed, you can put it here at 16 megahertz or 20 megahertz oscillator. So right here you can multiply it, and you can select with this multiplexer right here. You can select via these 2 pins coming from other registers if you want to select this high frequency or the standard frequency. Now the oscillator, the internal block starts here, because right here we have the 500 kilohertz oscillator, which goes to the high frequency PLL or phase lag loop, and with that one you can create those high frequencies. And from here you can select also the 500 kilohertz, which goes here. The prescaler is divided. It's a divider or a frequency division module that prescales the frequencies. This is why you get the highest, and then using flip-flops they divide by 2 in cascade, and that is how you get all those frequencies. And also there is another internal oscillator, this one, 31 kilohertz, which is used for low frequencies, and it goes here to the multiplexer, or it can go to the watchdog timer and power up reset timer. Also you have here you have another internal oscillator fixed at 600 kilohertz. It is called FRC, and this one goes to the ADC and other peripherals. The ADC is the analog to digital converter, okay, that requires a clock. So notice that the modules, all this clock uses multiplexing techniques or multiplexer modules with these pins. These pins that you see here are called IRCF from this register, and these are the bits that we are using, bits 0 through 3. So with 4 bits, the multiplexer selects 16 channels. Of course, we don't have 16 here, but we have about 8. But you need anyway. You need these are 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 here. So, but we can select up to 16, and we are selecting 11 different frequencies. Those frequencies go to another multiplexer where the register SCS, select clock source, with bits 0 and 1. These 2 bits selects when both bits are zeros, selects this input. When this bit 1 from SCS is 1 and the other one don't care, we will have the internal oscillator, the frequency from this module. Okay, and now all those frequencies go to the CPU and peripherals. There's also a sleep function which can stop all those frequencies. Okay, now let me go to another part of this module, and notice that we will go to page 89. Now, all the internal oscillator, it has 2 registers to control these functions, and this is known as the OSCON. So this register, the OSCON, is very important because you have to configure it to determine what frequency you want to set up the oscillator. So notice that you have these 8 bits from bit 0. These are the functions SCS, bits 0 and 1. Okay, this bit is unimplemented. Right here you have 4 bits, the IRCF, which we mentioned a moment ago, the bit 0 to 3, and the SPLLN bit, the most significant bit. So the way they operate is just below this register, which is in section 5-1, okay, for your data sheet. So right here you have the function of those bits, like bit 7, and now let's see bit 6. So notice that in bit 6 to 3, IRCF 0 to 3, I am highlighting in blue the code for 4 megahertz. So you have to select this code and write it into that register to set up the frequency, the internal oscillator frequency. Select bits to will select this one if you put this code 1101, okay, only for those bits, for these bits, and we are referring to these bits, IRCF 1101. That's what you have to write there. Okay, the other bits, SCS, these ones, with 1x you select the internal oscillator block, okay, so 1x for bits SCS. So an SCS is right here, right there. So you put a 1 here, and for the x you can select a 0 or a 1, because the x is I don't care. So 1 0 will be your combination, and 1101 will be your code to work at 4 megahertz. So that's something we don't have to forget, because we will use it when we get into the programming this microcontroller clock. And there's another register, oscillator status register, where you can program the phase lock loop and other features, depending if you want to multiply the frequency times 4, okay. So these are features that you can read, but I don't think we will use them in this course. Another thing is the OSTUN register. That one, don't change it. We will leave it as 0. So every time you see OSTUN, we will make it equal to 0, because this one tunes the frequency. So you can increase it or decrease it, but it's better to leave it at the calibrated, at the factory calibrated frequency, which is all the zeros, as you can see it here. So don't change the OSTUN. And this is table 5.3 is a summary of all these registers associated with clock sources. Okay, and I think this is the most important thing about these registers, about the clock module. And I will let me show you. I want to show you. I still want to show you one of the. Let me go here to 80 in the internal clock sources. FRC right here. If you're going to work with if you're willing to work with in a ceramic resonator, figure 5.4 shows you 5.4 shows you the way to connect the ceramic resonator with 2 capacitors, a series resistor, and a parallel resistor. You can check those values there, and that's for ceramic resonator. But if you want to work with a crystal oscillator, which is the one we use frequently in industrial applications or in high precision clocks, you don't want the clock signal. For example, you are designing a digital watch, digital clock, you need a very precise frequency. So this quartz crystal, it can be rated at 4 or 8 megahertz, 22 picofarad capacitors, 1 series resistor, which most of the times is within 2 or 10 mega ohms, and RF that's internally connected in the PIC micro. So then you will select in the registers, you will select the option that you are willing to work with an external oscillator, not an internal oscillator. Okay, so that's all for this topic. Thank you.